All right, we are going to go ahead and dive into continuity as well as the intermediate value theorem. So you'll notice through the slide deck I have everything, it'll kind of be sectioned off. So we'll do a little bit and then you'll do some practice on your own and then you'll watch the video to check your solution to see how you did. So please try to keep it in that model of when I say like try this one on your own, you try that one on your own, check the solution and then jump back so that instead of just watching that first, so it can feel as much like being in class as possible. All right, so we're going to start with continuity. And this is something that we talked about last year in pre-calc. Not one-sided limits, but continuity. And the big thing that the big takeaway in pre-calc with continuity is that if you were to put your pencil down and trace your pencil along a function, you wouldn't be able, a function is continuous if there's no need for you to pick up your pencil during that time frame. So as long as you can just kind of cruise along that curve and never have to pick up your pencil to like get to another part of the curve, then you know that you have a continuous function. But now we need to kind of calcify that. And that's going to happen a lot. We're going to take some concepts that you've been working with for in some instances since you were little, and show you now why that works and the calculus behind it. And we're going to have to support these things with calculus. We'll no longer be able to back them up with just because we said so type things. We're going to need to be able to verify those with limits and all that good stuff. Calculus. So the definition of continuity, now that we're in calculus, and it actually looks pretty similar. I think some of us actually looked at this before. And we're talking about, right now we're talking about at a point. So we're analyzing specific areas where a function may not be continuous. It needs to meet 3 criteria. First of all, f of c must be defined. So f of c is defined, which means that we don't have a hole at that value. It has a solid filled-in hole, or not a hole, filled-in circle. The next is that the limit as x approaches c of whatever that function is exists. And just as a reminder, to verify that a limit exists, we need to prove that the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x. All right, and then our last one is that this limit equals whatever f of c is, because I'll show you what that relates to in just a minute. So let's say we had a function and at c, so we have this and then we have a hole at c and then it keeps on going and then it's filled in right here. So this function satisfies the first condition. F of c is defined. It's defined at whatever this value of y is, right? The limit exists because they're approaching the same values, but this is not a continuous function because the limit, whatever that output is, we'll call that L, is not equal to whatever this is, we'll call that A. So this limit value does not equal what f of c is. So what we need instead is for that final criteria to be met, and that is f of c needs to equal whatever L is, whatever that limit is. And then we have a continuous fluid function. Continuity on an open interval is a little bit different. And one thing that we need to just keep in the back of our head when we're talking about continuity in open interval is that, so we have some of these functions that we can say their function is continuous because embedded within their function is some type of discontinuity. So we may still call them and treat them like continuous functions, even though they're not technically continuous at every point, which is why it's really important that we kind of break down this continuity at a given point more so than anything else. But what we say for an open interval is that a function is continuous on the open interval AB when the function is continuous at each point. In the interval. So we say that's continuous everywhere. Apologize for, I don't know if I said this already, my bad handwriting. It's for some reason when I'm using my Mac, it's not as nice, and my laptop obviously died at the end of your class. All right, so the last one we're gonna look at, oh, sorry, let me backtrack. So there's a couple of situations that we could have, and you saw these again in pre-calc as well. We could have a removable discontinuity. So a removable discontinuity could be something kind of like what we saw before. We could have an open circle and then it can continue on. So at C, our function's discontinuous because we have that removable discontinuity. So we could have something like, and this would be from like A to B. We could also have something similar. So we still have that same C value. We're looking on A to B. This is at C, but at that point, let's say we filled in a hole right there. So this is a removable discontinuity. This function would not be continuous on the open interval A to B. Another spot where it could not be continuous is if we have a non-removable discontinuity. And there's two types of non-removable. So we could have what we call a jump discontinuity. Notice that this is more than just, this is A, this is C, this is B. This is more than just a almost continuous function and then just one hole taken out. We're like riding along this, and then all of a sudden to get down to this, you have to jump off and go down there, which is why we call this a jump discontinuity. The other type of non-removable discontinuity is if we have an asymptote. And these are the functions I'm talking about. We generally call these rational functions continuous functions, even though they are discontinuous at this value, because it's embedded within the function. And that's really not, it's very theoretical and kind of out there, and not totally, like you don't totally have to have that rationale set in stone there, but I do just want to make that comment. All right, the other piece of this is continuity on a closed interval. And for continuity in a closed interval, we have a function f is continuous on AB if, when f is continuous on the open interval AB, so that's following the previous theorem, and the limit as x approaches a from the right of f of x equals f of a, and the limit as x approaches b from the left of f of x equals f of b. So this is just making sure that we don't have a situation. So let's say we had a function. Now we're looking on the closed interval. So let's say we had a function like this. And let's say this is B and this is A. And then it just so happened that at that point A, where we were closing that interval, f of a is a different value than the limit as x approaches a from the right. We can't just say the limit as x approaches a because there's nothing on the left to analyze. And so we have to say just from the right so that we have something to analyze. And again, when we're coming from the right, we're looking at all the values as I approach from the right. So for this to be true, we would have to take that guy right there and make sure that it is this filled in hole right here. So that from A to B, every single point on there is continuous. All right. So the reason why we care about continuity, and the big takeaway with continuity is this definition, because in order to show an open interval, continuous on an open interval, and therefore on a closed interval, we need to be able to solidify that at every point we have a function that's continuous, or at every point on my function, there's continuity. The reason we need to be able to do that is for the intermediate value theorem. So the intermediate value theorem is also something that we discussed, that we then in our intermediate value states that, and we're going to call this IVT, and this is an existence theorem, which means that this theorem is going to tell us that something exists, but it's not going to tell us how to find that value. It's just going to say that that value has to exist. And we're going to have a few of these existence theorems. IVT, MVT, and EVT, as well as the fundamental theorem of calculus, are like our 4 big theorems that we need to have for this course. But for this first half, IVT, MVT, and EVT are going to be our big ones. So this is a big theorem that's assessed on the test. So we want to make sure we really understand what's going on here. So this theorem states that if f of x, or if f is continuous, so that's why we needed that definition of continuity, is continuous on the closed interval that should be 2 words, AB, so f as AB, f of A does not equal f of B, and K is a number between f of A and f of B, then there is at least one number C in the closed interval AB so here going on here, our theorems are going to work this year. We need to know what the conditions are first. So what conditions need to be true in order for our theorem to apply? So first of all, our function needs to be continuous on the closed interval A to B. F of A cannot equal f of B. And K must be some number between f of A and f of B. So let me just summarize those. Our conditions, in order for this function, or in order for this theorem to even be applied, first of all, we need to have a continuous function. Second of all, f of A cannot equal f of B. And thirdly, we need to have some K value that falls between f of B and f of A. So it needs to live somewhere in between there. If that happens, if these 3 conditions are met, then there exists some C value such that f of C equals K. So it's going to be really important that you not only know these conditions, and remember you did if-then statements, the conditional statements. These were like your hypotheses, or your hypotheses, whatever. So that's that first part. And then our conclusion, therefore, is that f of c can equal k. This is why you did proofs. This is why you did if-then statements in geometry freshman year. So let's take a look at an example. So we want to know, I'm actually going to go to a new page. Does f have a c value in the interval 5/2 to 4 such that f of c equals 6? If so, what is c? All right, so first we need to know, does f have a c value on this interval such that f of c equals 6? So this should be kind of our radar that we're applying the intermediate value theorem. So what we're going to do first is we need to make sure, oh, and I need to tell you the function. Our function is f of x equals x squared plus x all over x subtract 1. So the first thing you want to check, looking at this function, think about rational functions. We have a point of discontinuity at x equals 1. So the first thing I need to check is, does 1 fall between 2.5 and 4? It doesn't. So this function is continuous on my closed interval. So that means that my continuity checks. So I'm just going to write myself a little note. I know that it's a continuous function. You don't have to do anything more than that. We don't have to show the limit and all of that. If it's an implied function like this, it's not a graph, we can just go ahead and do that little like mental check. Unless it has like a part A that tells you that you need to show that it's continuous. The next thing we want to do is we want to find f of 5/2 and we want to find f of 4. So f of 5/2, I'm going to go ahead and sub in here, would be 5/2 squared plus 5/2 subtract 5/2 subtract 1. I'm going to go ahead and simplify this down, and I'm going to actually go through the math of this because this is a question that you would not have a calculator for. 5/2 subtract 1, I can simplify that quite easily. That's like 5 over 5, or sorry, that's 2 over 2. So we would get 3/2. And now I see that I have a common denominator of 4, so I'm going to multiply my numerator by 4 and my denominator by 4. So that's going to leave me with 25 plus 10 all over 6, which gives me 35 over 6, or 5 5/6. Then I'm going to do f of 4, so I get 4 squared plus 4 all over 4 subtract 1, which is 16 plus 4 over 3. So I get 20/3, or 6 2/3. So what I need to check now is 6 between 5 5/6 and 6 2/3. If it is, then I'm good to go. And it is, right? It's between, that c value is between f of 5/2 and f of 4, or my f of a and my f of b. So that works as well. So before we go and find that we're going to say f is continuous on 5/2 to 4, my closed interval, and f of a, or f, you could say f of, 5 5/6, f of 5/2 is less than 6, which is less than f of 4. Therefore, IVT applies. So in AP Calc, we're going to have what I call one-liners whenever we're using a theorem and we need to show that the conditions apply. If you've taken AP Stats, this is not an AP Stats course. This is those you really need to like write long justifications. These are one-liners. If you're writing more than one sentence, generally you're writing too much. So for those of you that aren't wordy, this is like your heaven. So now let's find that C value. So to find C, I need to set my function. So I need to find f of C such that it equals 6. So I want to find the C value. So I'm going to let my f of x function equal 6. So I'm going to say 6 equals x squared plus x all over x subtract 1. I'm going to multiply each side by x subtract 1 to get that x subtract 1 out of the denominator. So now I have 6x subtract 6 equals x squared plus x. I subtract 6x, I add 6. I end up with x squared subtract 5x plus 6. I go ahead and I factor. I get x, what is that? Subtract 3, x subtract 2. So I get x equal to 3 and x equals 2. Notice that I got 2 answers here. Since I got 2 answers here, I actually need to go back. I need to backtrack a little bit. And I need to take a look at what my original domain was. So my original domain was between 5/2 and 4. Well, 2 does not fall between 5/2 and 4. So although that may be true, it's not within my original domain. So my answer would be C equal to 3 because 3 falls between that. The reason this intermediate value theorem works is because what's happening here, let's just draw a similar function. I'm just going to do 1 over x. What we're saying here is we're saying that if we know, if we look on a certain domain, let's say, we'll just say from A to B, we know that if there is an output, let's say at 2, right? Then we know that from here to here, even if a whole bunch of craziness happens, we have to have passed by 2 at some point. So if f of a is greater than this value, which is then less than this value, so notice this 2 is sandwiched between my f of a and my f of b, then we know that at some point I had to have passed by that output of 2. So there has to be some corresponding C value that gives me 2 out. This is similar to, so IVT relates very closely to driving. So if you're on the highway and you are going like 20 miles per hour, or I hope you're not going 20, let's say 65 miles an hour on the highway, you know at some point you had to have been traveling 20 miles per hour, right? Because you had to have gotten onto the highway somehow. So from going from 0 to 65, at some point you had to have passed by 25.